Welcome to the practical part of the multivariate analysis. In this part we deal with two scripts. The first script describes a couple of general analysis methods for multivariate case, like multivariate outlier checking, and the second script describes the principal component analysis. So you have the session 4 script explained .r and the session 4 script for PCA. We start with the session 4 script for explanation of general diagnosis and analysis. First, as you know, you set your working directory. I can quickly jump over that. You're used to that now. And then we load a couple of libraries that we will need for multivariate analysis. What we first do, as what you have seen on the slides, we draw samples from the normal distribution. We set the seed. That means that the random samples that are taken here, so the function rnorm samples 100 values with a mean of 10 and a standard deviation of 2 from the normal distribution, and we do this 5 times, so we create 5 random variables, and to execute this in a reproducible manner so that everybody who executes this function obtains the same result of the random number generator, we use the setSeed function. Then we combine these different variables into one data set, and what you've seen on the slides, we draw the ellipsoid around the Malebus distance. So you see here, these are the different data points that we have for just 2 variables that we have created, and one of the points would lie outside of the Malebus distance, or in fact 2 points, the point here below and this point here. And we've discussed in the lecture already that the Malebus distance, as pointed here, is more, as drawn here, is more suitable to detect outliers, joint outliers, than any other individual variable outlier checking method. Okay, for 2 variables that's straightforward, but we want to look for outliers that are related to the full data set, which is 5 variables here, so we can't plot these 5 variables in 5 dimensions. So what we do now is we draw samples from the random normal distribution. To do this, first we create a data frame with random data and use this to estimate the empirical covariance matrix we have encountered. We've discussed the covariance matrix on the slides. That's basically the matrix that provides the covariation between 2 variables, and in the diagonal the variance of the individual variables. That's called sigma. And we can check that the variance of individual variables, when you think back that we created here variables that have a standard deviation of 2, so we should have a variance of approximately 4, and if you look at these variables we see in the diagonal, we have approximately a variance of 4. Of course, these are random variables, so that doesn't match exactly the value of 4. Then we can calculate the correlations. We see that most correlations of these random variables are relatively low, and that's to be expected because these are just random variables that have been created. And what we do now is we draw a sample from a multivariate normal distribution using the function mvrnorm. That means it's the multivariate random normal distribution from which samples are taken. We take here 200 samples. We have the mean that we use here is, if you execute this, it's a mean vector apparently. So since we have 5 dimensions, the overall mean is in any dimension is 0. We need to provide a covariance matrix to inform the function what correlation structure the data has, and we do this by providing the sigma that we just created. And empirical equals true. And as always, you find all information on the functions in the help files, and you can see that empirical equals true is the empirical covariance matrix. See a couple more information here. Okay, so we draw the sample. So what we obtain now is a 5-variable data set with 200 rows. These are the individual samples that we just drew from the normal distribution, from the multivariate normal distribution. So to conduct an outlier test now, we can use the function moutlier, where we provide our multivariate object and define a quantile for this outlier checking. And you can see here the individual values from this function that we obtain. The plot has disappeared here. And we see here the classical Malnobis distance that is calculated here, the robust Malnobis distance. A robust Malnobis distance means that the outliers are basically not included in calculation of the Malnobis distance, because they would otherwise increase the distance itself, or influence the distance itself. So the mean vector when you calculate this. So in case of quantile here, we can define what we define as outliers. So it could be 95% quantile or 99% quantile. In the case of the 99% quantile, which we have defined here, we'll expect approximately 2 outliers. So we see that we only have 1 outlier based on the robust Malnobis distance, and it's actually relatively close to this threshold, given the threshold that we provide for the 99% quantile. So now we set back the parameters for the graphical window to having just 1 window. Here you have some code to reproduce the slides, and we continue with the graphical assessment of multivariate normality. We do this, and this is the plot that we obtain for the chi-square distance, and you see that, not surprisingly, the data are fairly well normally distributed, multivariate normally distributed, so the quantiles and the orders robust Malnobis distances match each other quite well. This function, if executed like that, you have an interactive tool, so you could use this cross here to remove points and replot discrete chi-square distance. For example, we could remove this point, we could remove a point here, remove this point, and this recalculates every time the chi-square plot to assess the multivariate normality. Check at the output of R, we see which observations have been removed, and you could later on evaluate whether you would really like to remove that one from the data set. So with a right click, you leave this tool. You can also execute this function without the interactive tool, so that just means you add the argument ask equals false, and then you are not, as you can see here, there's no interaction possibility. Quant, this function allows the user to evaluate the quantile that is used for the center of the whole data points. If you choose 1, all observations are used. If you choose 0.5, you choose just 50% of, you include just 50% in the calculation. Then I have an extra session here that shows you how the deviations look if you have a relatively small sample size for the data. So if your N to P relationship is smaller than 25, so if you have less than 25 observations per parameter in the model. So in this case, actually, you have a more extreme case that we deal with. Briefly show this. So we have just 15 samples from a multivariate normal distribution, but 5 variables included, and then this looks much stronger, much less multivariate normally distributed. So you see, even if you draw samples for them from multivariate normal distribution, if you have just very low sample size, then you will find quite some deviation, or you may find quite some deviation from the multivariate normal distribution. So that's it. Here you see some more code to reproduce the figures on the slides. And with that, we jump directly into the PCA, part, the PCA part. See also here, this is all commented, this is the code to create the slides. You can jump directly here to set a working directory. Again, I'm not going into details here on how to set working directories. You've learned that before. If you just execute this script, you need to load the vegan library and the MV outlier library, which you have already loaded before, so we wouldn't necessarily need to do this. And we work here with the data varchem, that's environmental data of soils. So we loaded the data and have a look at the data. So you see that from different soil samples we have measurement of ions, of the depth of the humus, of the pH value, and of the fraction of bare soil. As usual, you can use the help to learn more about the data set. So you see here some more information, and you see a paper from which this data comes from. So read the paper if you are more interested in the data. We will just use this as some example data for our case. So first we check the multivariate normality using the cheese-plot, and we see there is a little bit of deviation, but we don't have a large sample size here. So some deviation is expected, and it's not particularly worrying to us because our main aim is here to represent the data, to visualize the data, and we are not doing statistical hypothesis tests where any deviation may be more problematic. So we run the principal component analysis. You see here that the function is pretty simple. It's just RDA, the data, and then a scale command. This argument, it's not the command, the argument scale equals true provides information to the function that the data should be scaled to unit variance and centered to the mean. So, as discussed in the lecture, you should always scale the data unless the descriptors have the same order of magnitude. When we run this, we obtain this result. The inertia is 14, that's the total variance, and that's not surprising because if we standardize the data to the standard deviation of 1, and we have a variance, each of the variables has a variance of 1, so if we have 14 variables, then our total variance is 14. Then we see the eigenvalues for the different axes. These are the absolute eigenvalues. We obtain a clearer picture with some additional information if we run the summary function. Summary function, you see the cumulative proportion for the eigenvalues. And you see that, for example, the first two principal components, those are typically plotted, they explain 60% of the variance in our data. And if you just look at individual axes, we see that the first principal component explains 37% and 22%. And if we go to principal component 8 and higher, they only explain 2 to 0.0 something fraction of variance. So let's now plot. We first plot the sides. And we know now that principal component 1 is a little bit more important than principal component 2. We also see this here if we see the length of the gradients. It's from -1 to 1, principal component 1. That's somehow, and it's from -0.5 to 0.5 on the PC2. When we look at the distances, so the interpretation we've already discussed in the course, the differences between the distances between two sides indicate how close they are. So this would mean that the variables that are measured in side 10 and side 13 have relatively similar values, and the values of variables that have been measured of this descriptor in side 24 and in side 5 more or less have the maximum distance of all sides. So why is that? First of all, the distance should be maximum on the first principal component. That would be somehow 24 and 3765 all have similar distances. And if we also include the distance on the second principal component, and we see that 5 has more or less the largest distance to 24. We can also check the total variance, as we discussed before, that is 14, because we have scaled our variables. We have 14 environmental variables, each with a variance of 1. And if you wanted to extract eigenvalues, you can do this with this elements of our objects, is VA underscore PCA and the CA and eigen element of this object. If we sum that up, not surprisingly, we see that the total sum of eigenvalues is also 14. So now we move to the next question. How many axes are needed in our principal component? How many principal components are needed? So we have discussed the sum criterion. You set a sum here of 70% for the alpha. And then we take the summary of the PCA and look at the different and ask how many axes we need and whether the value is larger than 70%. And we see that if we have just 2 axes, we don't yield 70% of explained variance, but once we include the third principal component, our data explains already 70% of the variance. So if you would just execute this part, you would see we have here the eigenvalue proportion of explained variance and cumulative proportion. What we extract here is just the third row, so the cumulative proportion, and compare this to the 70%, and we see with this third principal component we exceed the 70% criterion. You could also use a Movieplot. In the Movieplot we plot the different eigenvalues against the number of principal components. So we do this here. And what we look for is something like a clear elbow, where we see that there might be a point where we have only a minor decrease. So we have very strong drops in the inertia in the explained variance, and at some stage that is leveling out this decrease. So these are fairly similar, and you would probably here choose also 3 or 4 or 5 components based on this Movieplot. As we have discussed, this type of plots are somehow more subjective form of choice. So whether you define that this Movieplot indicates 3 to 5 of the principal components, it's rather a subjective choice and depends also on your objective of the study. We can also apply the broken stick criterion. That's done here. So we plot above the ordination variance, we plot the variance that a broken stick, if you have this random broken stick model, if you would have that, then 3 of the principal components would explain slightly more, or the third principal component would explain slightly more than the third one from the ordination, and you could evaluate or assess, come to the conclusion here that if a random breaking of a stick would lead to more variance on the third axis than in our data, then the amount of variance in the third axis is less than you would see from random data, then it's perhaps not that meaningful. But again, it depends very much on the scope of your study. And if you can include several variables, if your aim is not just to display or visualize the relationships between sites and descriptors, but you also want to conduct a follow-up analysis, for example, principal component regression, then you should include more principal components that may be needed than those that may be needed under the broken stick criterion. So different way of using the broken stick criterion is provided in the library Biodiversity R. In this library that features a couple of functions for biodiversity analysis, you have a more informative output of the numerics. We see here the broken stick, the cumulative broken stick, and the individual broken stick provided. So we see that if we focus on the individual broken sticks, then we have only 2 axes that taxes the 2 principal components that exceed the amount that is explained by principal components derived just from a broken stick model. And if we look at the cumulative proportion of random stick, then we would actually include all first 8 principal components. We have an extra, I provide you with an extra section here that shows you how you run this principle, this prognostic model. I'm not going into details here, that's explained in the text, and it's only for those that want to know how this prognostic model really works and how you can calculate this simply for yourself. The final technique that we have here is cross-validation. We've encountered cross-validation before in the course, and we will use the function here to run k-fold cross-validation. K-fold, we will use here 4-fold cross-validation, so we set the seed again so that we have a reproducible result, and you see that this takes actually a couple of seconds to run this function. So this is done as follow. The data are removed using this function. So you provide here an amount how much of the data is removed. If here 25% of the data are removed in one stage, it means you have 4-fold cross-validation, so you always use the remaining 75% of the data to estimate these data. Then you have the number of simulations, how often this is done. This is done here, and this for this function this is now done 100 times. That's why we have to wait so long. And a couple of other arguments that are explained here. So if we look at the results, we see that based on this criterion we should choose based on the mean sum of prediction error, the mean squared error of prediction. Then we search for the minimum, so that's the minimum error per predictor in the model. And we see that if we have two predictors in the model, then based on the mean square per predictor and mean square error per predictor, then having two of the predictors in the model yields to the minimum, although even with three, the results are very close for 2 and 3 predictors in the model. So you could also use this function if you have missing values in your data set. That's explained in the function impute PCA. And there's another function which you can use for cross-validation. If you, for example, are interested in the total amount of explained variance that is conveniently provided in this functions, and for this, the function requires a fitted PCA object from the function print comp, so it doesn't work with the vegan object, although the result is exactly the same if we look into the x.rpc. So if you compare this to the vegan result, it's exactly the same. You see here also some design differences. In vegan you have the variance provided. Here we have the standard deviation provided per component. So these are these are the square roots of the eigenvalues. We could simply use the square of this, and then you would have the same results as for the RDA function. So we continue, calculate PCA here, and what we obtain is this plot. So you see the number of components included in the model against the total explained variance. It's of course clear that if we have 14 components included, then we have a total amount of variance. The R square is obviously 1. So you see here that we have a slight decrease, and you could base your choice. If you're interested in prediction, you can base your choice on this graph as well and see how many variants we have explained when we decide on a chosen number of components. Other elements of this function, scale equals true, is also the same information as we discussed for RDA. We have the segments function. Segments means here number of k-fold, so it's 4-fold cross-validation as in the previous function. And we have the argument plot.opt equals true, which means that we plot the results. So when you use this function, note that it has a little bit different strategy of conducting the cross-validation, whereas in the previous function we randomly nullified or set missing values in 25% of the matrix values. Here this works much faster because we just take 25% of the rows and exclude them in the fitting of the PCA and then predict them all together. So we do the outlier checking. We've discussed this before. Select here a quantile of 79%. And you see here the score distance and the orthogonal distance. We see based on the orthogonal distance we have one outlier. However, this outlier is not at the same time does not have a large score distance, so we don't worry much more about this point. It's side 11 in row 23, and we've discussed outliers in the lecture. So we can now plot a B-plot, set the variables back, this argument we set the plot window back to one plot per window. Then we plot the B-plot. I'm not going into details here on the scaling in B-plots. That is discussed below regarding the access scaling, the vegan documents, and you should execute this and load and read through the documentation for this package. So we plot the B-plot. So now we have a plot that shows you again relationships between the sides. We've already seen that before. And apart from looking at the relationship between sides, we can also look now at the correlation between components and variables. And you would interpret the plot like this, that if the arrows are into the direction of a side like 24, then you can assume that these values are elevated in this side, whereas if you have the opposite like this against n, then you would assume that there's less nitrogen in the soils into this direction. And the same is the interpretation for the other arrows. If we look at the angle between arrows, then you can read the correlation. So if you have a 90-degree angle, that is basically a zero correlation. If you have a completely opposite arrows, that means that your correlation is more or less -1, and all other results are in between that. Yes, after we have now inspected the B-plot, we will deal more formally with the questions such as the choice of the number of axes. Now we've done this already, we will have to deal with the question of the variables, how they load on the axis, and you can calculate the explained variance for different variables with this PCA var explain function, and that shows you which the amount of explained variance of the different variables for the two principal components. You could also do this. The A indicates the number of total principal components used, so you would see here which variables have the highest contribution to the first principal component. Can't do this for individual axes, always the cumulative R square on all on the axis. Obviously, if you choose 14 principal components, then you have an R square of each for each of the variables, because overall we explain this is the total variance in the data set that is explained by the 14 variables that we had initially, and now we have 14 principal components. If we want to look at the loadings, and just a note of caution, loadings are interpreted here in R. Loadings indicate the eigenvectors, whereas in different contexts they may indicate what we consider in R as correlation loadings, so the correlation of the original variables with the principal component axis. You see for this object loadings, only the loadings above a certain threshold, 0.1 I assume, are displayed, the other loadings are not shown. The same, you see the same for the object. This is the XRPC object that, remember, we needed to run two different principal component analysis functions to enable the use of different analytical functions. So the analytical functions like that we use for outlier checking or PCA variance explain relies on objects from the principal component function, whereas we otherwise can use the RDA object for different purposes. We use this later on in the course, so that's why we use the RDA object here too. You see that the values, though, are the same. If you look here, the loading of phosphorus on component 1 is minus 35.6, and that's equivalent, or that's the same as here. It's just rounded. These values are rounded values. We have another value. Let's check another for aluminium, 0.116. So this is rounded. These are rounded values. You see that we obtain the same results for both functions. We can also check that we know that one of the conditions in the principal component analysis is that the matrix of eigenvectors multiplied with the transpose of this matrix yields the diagonal matrix. We see that this is actually true, so along the diagonal we have 1, and if you look at the power, so the exponent for these numbers, you see it's not precisely 0. These are just rounding errors. Y doesn't add up to 0, but basically we have zeros along the remaining cells, in the upper and lower triangles above and below the diagonal. And yes, because of rounding errors, then we have extremely tiny values, that the values are not exactly 0 in these cells. We can compute the variance of individual variables. Again, that's not surprising that we have here all variances of all individual variables is 1. And then I provide you with a function. I just took this function from the internet, from a website. That's a convenient wrapper to calculate the variable loading. So this function just multiplies the loadings with the standard deviation of the eigenvalues. So we apply to the loadings, and 1 just means that we do this column-wise. We apply the function that we've just defined here and use as input the standard deviation from the object. The standard deviation we assign here, it's the standard deviation. Just have a quick look. These are the standard deviation of the eigenvalues for each of the principal components. So we run the function, and now we have more easily interpretable results. We see that the component 1, we have different variables that have a high correlation with this component, for example pK, calcium, magnesium, sulfur, zinc. They have all correlation coefficients above 0.75, so they have a relatively high correlation. We can check that this is true by extracting scores from the PCA. So the side scores the principal component scores we've discussed in the lecture. See here how you extract them in R, and when we correlate now the scaled variables with the scores, we see that we obtain the identical results. So we can prove that this is really the regression coefficients, the correlation coefficients, when we multiply the loadings from the axis with the eigenvalues, the square root of the eigenvalues. Yeah, another issue that we discussed we began discussing in the context of multivariate regression analysis, and we discussed also for PCA, is, as you can see here, if we look now at the correlation coefficients, we see that we have many variables that are associated and have a correlation with the first principal component, and that doesn't make interpretation very simple. So ideally, we would limit the influence of variables with low correlation on the individual principal components and just have a few variables that have a higher correlation, and we can run a so-called sparse PCA where we put a penalty term on the eigenvector values, on the loadings on the axis. This has been shown in the lecture. First, as you know from the lasso, we need to find the optimal penalty term. This is done here with an objective function. I'm not going into technical details here. What we provide to this function is, on the one hand, we scale our data. We've discussed this before. We need to have the same variance in the different variables. Kmax means it's the maximum number of considered sparse PCs. We have identified two principal components as being ideal before, so we provide k.max equals true. And then we provide here a method that is used to estimate the variance. That's here the standard deviation. Yeah, have a look in the function for other options, for example, for other methods that you could use, like the median, the multivariate median, or other values. we first obtain the output that is the same as for the principal component function. We see here that we have the eigenvalues for the two axes. And then we obtain here for the optimal selected variable, we obtain the loadings of component 1 and component 2. And we see that now the loadings for 7 of the variables have been reduced to 0, and the loadings on component 2, actually most of them have been reduced to 0. So it's much easier now to compare component 2, which is mainly a gradient and axis of aluminium and iron, and has a negative correlation with bare zone and humus depth. So the choice for the selection of this optimal value, we can look at different plots. So first plot, here is for each of the principal components. We see the explained variance against the sparseness, that means the number of components that have a value of 0, where the loadings are 0. We see where we have, and that's actually the selection which we see. If we have 7 of the loadings for the descriptors that are 0, then we reach an optimal value, and we obtain the value for lambda, that's the penalty term here. We obtain a value of 1.75. We see here the estimated cross-validation error. We see as well the number, again here the number of descriptors that are contained or that are 0. And this is here given for here for the optimal value of lambda for the second axis, and we have here this is for both axes together for the first two principal components. No, excuse me, that's not the cross-validation error, it's of course the cumulated variance of the PCs. It's here 32% for the first axis, for the first principal component, and here 52% or 51% is explained if you take both the first two axes. We can also plot lambda directly. So we see here for choices of different lambda, we see the development of the explained variance on the first axis, and we see the same for the second axis, and the optimal choice based on the objective function, and you could look at different details. Now we use these optimized lambda in the SPCA grid function to compute the sparse PCA, an object which we can use then. We have some more information contained in this object. You see that compared to the optimization function, we provide here the lambda as well, and we extract from this object the lambdas. We abstract the lambdas from this object that we defined before. We save this in the object SPCA. If we have a look into this object, we see it's an object that has 12 different attributes. You see the standard deviation for the two axes. We have defined two axes are fitted. We have several other information given, and we have, for example, the scores given here. And the class of this object is principal component object. That's similar to an object from principal component, from a class principal component. We have a look at the loadings. We can again compute the correlation. We see that through the sparsity function, we have actually an increase in the correlation with some of the variables. So before we had 0.8, now we have 0.92 for the variables phosphorus, calcium, magnesium, and sulfur, and manganese and zinc. Manganese has a low value, so if you would choose a higher lambda, then manganese would not load anymore on this component. And we see by contrast again that now component 2 is really a very strong aluminium and iron, has a very high correlation with aluminium and iron. We also see when we use this that none of the variables that has a high correlation with component 1 or 2 correlates with the other component, and that means they are more or less orthogonal. And this can be seen when we calculate a B-plot. In fact, we should put back the graphic window to default with just one plot for a graphic window. It's done with this function. And if we plot this, so first this looks a little bit strange. Now you have all variables plotted really in the same direction as the principal components, but it's somehow clear because we have now only correlations with, if you had the arrow like that, it would also slightly correlate with the other principal component, and as I said, since we see that the correlations are now 0 for the 4 variables with the component 1, then of course it is just parallel to the first or second component. It's not really easy to read in the B-plot now because all the variables that have a relatively high correlation with the principal component are plotted on top of each other. And finally, you could check the eigenvalues again, and it's done like that. The final issue is we could extract the principal component scores if we wanted to run the principal component regression. That's shown in this part of the script. Just quickly, you can extract the scores from the vegan package from the object using this function. So we obtain here the scores on the first 4 axes. And for the other object from the Sparse PCA, this could be done here with the scores in the scores attribute of this object. Fairly simple. You see here a little bit more text, a note of caution on principal component regression and on the choice on the number of variables and axes to use in the principal component regression and so on. But it's discussed more theoretically in the lecture as well, so I don't go into details here. You can just read this yourself. And I have an extra section for those that want to look a little more into it, where I show you how nonlinearity influences the principal component analysis and why different ordination methods are used. And then you have the exercise below, this extra section for those that want to look into more into depth. Then you have the exercise. So use the class data set in the library chemometrics, conduct a PCA, decide how many principal components are needed to visualize the data, extract the number of meaningful PCA axes and check the intercorrelate of the principal components. Check the intercorrelation of these axes. What do you think? What you could also already formulate an assumption of the correlation between these axes. And then have a look which variables are most important for the first axis and explore and redo the analysis for a sparse PCA. So that's it. I hope you learned a little bit about PCA and sparse PCA and about the different implementations in R functions, how you could use them, and hope to see you in another session.